Ooh, nice. All right. All right, ladies and gentlemen, thank you for attending the session on large system in AI. Our first speaker is, we're going to test this out now. If only AI could say his last name. We're going to welcome Dr. Papanicolau as our first speaker. He is the director of the National Lab for Agriculture and Environment in Ames, Iowa, and is a world leader in flow, turbulence, and sediment interactions, developing critical zone science. So, thank you.
Thank you very much. After having a very exciting morning session, I think we can use the afternoon sessions to get to more details, and hopefully, this will be worth of your time. So before I get started, I want to acknowledge also my co-authors, and there are many contributors, so I didn't have the space to get all of them there, but especially many thanks to Kesav Basnet, who is the ORI's fellow working on this. So what we're going to be talking is examples of AI use and system dynamics modeling. So I have to do a little bit of explaining here. It doesn't, it's on, but for whatever reason, how did you? Okay. Alrighty. So a little bit explaining here some of the jargons involved. We're dealing with an agroecosystem, and an agroecosystem has different components. You can see here production, ecology, economics, the human factor that in the past has been ignored, and then technological advancements. So dealing with that integrated domain here is very challenging, especially with the existing mindset, which is using single discipline models to address a problem that is multidimensional. And that led to the genesis of what we call systems models. If you remember from your linear algebra course, talking about systems of equations, well, it is something analogous. You have a lot of models representing each of those components, and somehow those models need to communicate figuratively and literally. What that means is that dimensions and the consistency across space, the unit space. Is it county? Is the farm? The plot scale? All of that has to be done in a seamless way. Therefore, to do that, we need, that's systems thinking, but to do that, we need the appropriate tools. Another challenge that kind of I addressed is, as I mentioned, and this is an example here, those bullets, that within an agroecosystem, you do have parameters or properties that are discrete. They occur certain periods of the year. There are continuous properties, deterministic, stochastic, instantaneous effects, time-delayed effects. Anyway, I will question this, but time-delayed effects, linear and non-linear processes. So again, we need a framework that can help us address this. Also, in many occasions and in my lab, as the name suggests, National Lab of Agriculture and the Environment, we are constantly looking for trade-offs between agriculture and the environment. We have the stakeholders coming and saying, well, we need to see more food production, intensive management, and then how all of this goes hand in hand with the nourishment of the environment. So in many cases, we need to look to find that what I call sweet spot, or identify those tipping points that can sort of derail one component or keep what we call that striking that balance. So looking for trade-offs, you need also a tool, and the systems dynamics model framework offers that capacity, which I'm going to explain in a few minutes. Another thing that I don't have here in the slides is the forecasting ability. We would like to use those tools to forecast what is going to happen if I make a management choice A now, how that management choice is going to affect the agroecosystem in the future. And to do that, you need to have that framework, but also you need to have data from the past, historic data, and present, to be able to do that forecasting. For those who are familiar about Monte Carlo processes, this is something analogous. So, let's see here. An example that we have looked using system dynamics model and organization of data is exploring the management choice of integrated crop livestock systems in the monoculture system of the US Midwest. And everybody, or most of people, are familiar with the sort of concept of circularity that integrated crop livestock systems can offer. But here, balancing food production and environmental quality and social quality, it can be a challenge, especially what we define as social quality, the labor that entails when you do integrated crop livestock system. There is also another alternate there, a more aspirational management approach, which is the integrated crop livestock with cover crops that allows you to increase the forage acreage, therefore enlarge grazing capacity in your watershed. So in doing so, we have used CASAV and the group there, an object-oriented language, and there are a couple of those that essentially that sort of integrated farming system here has modules, basically 5 subroutines that are communicating with each other: the cash crop, the livestock, the economics model, environmental quality, and social quality. And depending on the available literature, established literature, depending on the level of detail that we wish to strike here, we can have complex models, economics models. We can have simple economics models such as net income and based on inputs and outputs. The same thing applies for all other models here in that framework. And all of this here was done in Vensim, but can be done in other object-oriented languages. Vensim is by Ventara, is an industrial systems framework that has been developed to address, initially to address problems in engineering, but then recently, the last 15 years, 20, has been brought into ecology and agriculture in general. So with Vensim, we can develop a qualitative first model, like a conceptual model. And the red circles that you see here is those 5 models that you saw in the previous slide. And then the blue arrows that they have a certain direction and they have a certain sign, plus or minus, is indicative if the impact of a certain action is positive, if it is a positive outflux, or where is a negative? A negative outcome. And each of that black here sort of definition that you see is basically what we call a stock. And then you have the inflow and the outflow from that. And essentially what it is a mass balance sort of equation for each of those components. Now, in real life, how it looks, we can have an equation for each of those blue arrows that you saw in the conceptual diagram that is called causal loop diagram. And you can see here, I mean, you can have the level of detail, even you can incorporate lag times. So because, as I said earlier, an action can create reaction, but after a certain period. And obviously you need their data from the literature to be able to sort of establish that. So going through this exercise, we have looked in the whole state of Iowa, because we had data there, sort of the balancing act for 1, 2, 3, 4 management practices. This is corn only, crop only, that's corn, soybean. This is crop with cover crops, ICLS with cover crops. And we are assessing 3 components of the agroecosystem, the economic, and having an index there, the environmental quality, and we have an index, and then the social quality. And what you see here is for each of those components, for its indices, we're looking basically the performance of each of those management practices under no-till, strip-till, and conventional till. And for example, we see that ICLS with cover crops is the champion when it comes to economic return, does fairly well with the cover crops, the environmental quality, but when it comes to social quality and labor engagement, then things drop down. Of course, there are some caveats, such as, well, livestock requires certain times of periods that are intensive, and the other periods, it's more of a routine type of work. Anyway, so how good is the system modeling approach? This is a comparison of the systems model. This is totally, I moved away from the ICLS, and what I'm doing here is modeling soil organic carbon in Iowa for starting in 1900s, when we have industrialization of agriculture, all the way to 2015. And we ran initially Descent, which is the black line here that you see, to model soil organic carbon matter in a generic plot, hill slope. And down here you see we're plotting the erosivity, the t-value, erosion here, the t-value is there. So what we see is the red line here is the system dynamics model that we used for this specific problem. And we see a pretty good agreement. We see also that we are capturing those instances that we have, significant events, such as in 1985, that we had the Farm Bill, and then we saw a revamp on SOM. I'm done. Almost there. So why AI and systems modeling go hand in hand? Well, because we got all of those type of data sets. We need those data sets to be presented in an organized way. Sometimes we need to camouflage information that we don't want to become public. And therefore, this is why we need AI basically to play a supportive role into this type of multi-dimensional type of problems. And as an example here, this is data, N20 data, and we're talking about IRA, Inflation Reduction Act, in ARS, where essentially I have AI help me sort of group categorize data based on agriculture, reference conditions, and urban conditions for the N20 that you can find within, this is the hyperrheic zone of rivers, where you can find, this is the Lotic experiment that was ran for almost 15 years, and you can find basically, you can use those tools to generate, do trend analysis, and also, as I said, to identify provenance of the data. And I think I know we got ARS people here, so, but so I use always that slogan here that for every dollar invested in US agriculture research results in $20 of economic return. So, all righty. Well,
Thank you.
thank you.
We have time for one question. Yep.
All right.
Did you have
Oh.
a question? Anybody have a question? Oh.
Hi, so I feel very interested about how you introduce the system dynamics, but how could you please tell me your vision, like how AI can incorporate into the system dynamic modeling?
Primarily improving the data inputs. The system dynamics models can be empirical, semi-empirical models, can be also a typical model, with a continuity momentum equation where you do not need there a lot of data. So where AI can play a huge role is when you are dealing with a lot of those empirical equations, for example. And why? Because you can use a large amount of data very swiftly, and that can improve your input. And that's very important, especially for forecasting applications. So I have not shown here some of the analysis that we have done to look, for example, what is going to happen 100 years from now under different climate pathways, in terms of yields, in terms of environmental quality, name it. So it's improving, basically, it's a more refined tool to improve our data inputs. All right, well,
Thank
my
you
time
again.
is up. Thank you.
Thank you.